Any questions whatsoever about the last lecture? It was full of slips that usually tend to confuse people, so please ask questions. No questions? Okay. Okay, today we are going to discuss the using functional methods to analyze the structure of Green's functions. In particular, I will discuss three different generating functionals. Not a particularly good erasing job I did. For full Green's functions, that's our old friend z of j, which we've talked about earlier. For connected Green's functions, and for one particle irreducible Green's functions. Our immediate reason for going through this analysis is to derive the ward identities directly for one particle irreducible Green's functions and thus complete the renormalization program for quantum electrodynamics. However, the methods are of general utility and applicable in a wide variety of circumstances. I could have talked about them earlier. There's nothing especially quantum electrodynamical about them. It's simply that this is the first time we have encountered a problem of sufficient combinatoric complexity to make it worthwhile to go through this general derivation first. In order to simplify the notation as much as possible, I will conduct a discussion for a theory of a single scalar field phi. In a many-field theory, the only alteration is appropriately sprinkling the equations with indices. Therefore, I will imagine, and being a little bit careful, or more careful than I will be about the order of the terms if one is dealing with Fermi fields and so has anti-commuting sources instead of commuting sources. But those are both trivial matters. So we'll imagine a theory of a single field phi. It may be an unrenormalized field or it may be a renormalized field. As far as the combinatorics goes, it won't matter. And it has dynamics determined by some action principle, some action, S of phi. And I define S of phi and j as the original action plus integral d4x, j phi, where j is a C-number function of x. And, as you probably know by heart, the generating functional for Green's functions, for the full Green's functions, z of j, normal ordered function, not normal ordered, normalization factor, functional integral over phi, e to the I s of phi and j. To find a generating functional for connected Green's functions is of course trivial because of our powerful theorem of general utility that the sum of all Feynman graphs is the exponential of the sum of connected Feynman graphs, if there are no vacuum to vacuum, which is what we're considering here. And therefore, if I define the definition of W, the I is put in just to adhere to general convention. When general convention is arranged in such a way so that all the i's disappear when you rotate into Euclidean space, W of j, IW of j I should say, is the generating functional for connected Green's functions. That's a trivial remark and one I made, in fact, in passing in a much earlier lecture when we first introduced Z of j. Now, before I go on to discuss the generating functional for IPI Green's functions and how to construct it, I'd like to point out an amusing property of W of J, which could be described as counting loops and counting H-bars. We have, throughout this course, been setting H-bar to 1, except on occasions where it is convenient to restore it, and this is one of those occasions. So let me put the H-bar in and write Z of J equals N integral d phi e to the I S of phi and j over H bar. Now let's count. Of course, having put an H bar into the Lagrangian in this way, we've put an H bar into all of our propagators and vertices, and therefore an H bar into every Feynman graph. Let us count the powers of H bar associated with a given Feynman graph. Every propagator will yield a factor of H bar because the propagator is obtained by inverting the quadratic part of the action, and the quadratic part of the action has a 1 over H bar in it. Every vertex on the other hand will yield an H bar to the minus 1 because the vertices are just read off from the non-quadratic part of the action, and every non-quadratic part of the action has a 1 over H bar in it. Therefore, a given graph is proportional to H bar times the number of internal lines, because that is the number of propagators, minus the number of vertices. This is the old notation we used when we were counting divergence powers. On the other hand, for every connected graph, the number of loops is the number of internal lines minus the number of vertices plus 1. This is again an old result, but I'll briefly remind you of the derivation. You have a d4k for every internal line. You have an energy momentum conserving delta function for every loop. And therefore, all of the delta functions kill internal integrations except one that is left over for energy momentum conservation. And therefore, the number of free integration variables, or equivalently, the number of loops, is given by the formula displayed on the board. Notice I underline connected. If the graph were disconnected, it would have, if it had two components, it would have two overall energy momentum conserving delta functions, and the formula would not be true, one for each component. Thus, by some algebra, which I will leave you to do, this expression equals H bar to the L minus 1. Thus, counting the powers of H bar, thinking of W as expanded in powers of H bar, is equivalent to expanding W in number of loops in the graph. Notice it is a rather peculiar power series. No loops, which is sometimes called the tree approximation, because graphs with no loops are of the topological structure that are called trees in network theory, topological network theory. Tree approximation is H bar to the minus 1. One loop is order 1, 2 loops is order H bar, etc. Just to give you something definite to look at, let's consider we're working in with our old friend 5/4 theory and expanding W out to order h bar to the minus 1. We have the dots represent j's. Okay, that's a graph that's there. Then this is a graph that comes in, also to order h bar to the minus 1. And then I can get much more complicated graphs if I want to. There's one with sixth order in j, but still I order h bar to the minus 1, plus etc. Whereupon to order 0, I have, well, here's a typical one. That's also got 4 j's on it, but it's also order 0 in h bar. Notice I do not explain this expansion procedure. I explain this expansion procedure for reasons that will become clear shortly, but I do not explain this expansion procedure because I think this argues that things are a good approximation or a bad approximation. Expansion in h bar is a garbage idea. H bar is a dimensionful quantity, and we can always choose our unit, so it's 1. So there's no particular reason to believe in expanding in h bar as necessarily a good approximation. I just wanted to point out to you that if we did expand in h bar, this would be equivalent to counting the number of loops. Notice also that the number of graphs we have to work with in a given order are still very large. This series goes on forever. There are a large number of vacuum-to-vacuum connected graphs in the presence of J with no internal loops. Of course, there are only a small number of one-particle irreducible graphs, and indeed only the first 2 graphs are in any reasonable sense one-particle irreducible, and therefore this one can be cut, and therefore it would be nicer, even nicer, to have a generating functional for one-particle irreducible graphs, and I will demonstrate how to get that. Before I do that, are there any questions?
Are there 2 factors of h bar in the formula for cross-section?
Well, I haven't worked it out. It's a bit tricky. We've put an h bar in the j, so we've got a, let's see, the propagator has an h. Let's see. The propagator has h bar in it, so that means I've got to renormalize my fields by a factor of square root of h bar. There are no. This is order h bar the minus. No, it doesn't come out that way at all.
I've heard that the tree approximation is the classical approximation.
It's the classical approximation in the sense that it's formally the limit of this object as h bar goes to 0.
So there has to be no h bar.
In the cross-section. It depends on whether counting things this way, whether the cross-section is a classical object or not. I just don't know. We can talk about it privately and work out what it is. This is classical thinking of this as a field theory, not classical thinking of the classical field theory, not thinking of it as a classical particle theory. Okay, so there are additional h bars that come in transposing from field to particle language, as was discovered by Max Planck, the first appearance of h bar, and you've got to worry about those. Yes? Yeah, but this is a vacuum-to-vacuum matrix element. You have to be a little more careful. You can be a little more careful. I just don't want to, if you want to investigate those kinds of questions about cross-sections, but I just don't. Well, the easiest way of doing it would be just to write down our expression for the cross-section, and and see how many h bars you have to stick in to make it to make it bidimensional analysis. Okay, let's see. We know that, for example, we had just massless scalar particles. The cross section would have to be lambda squared e squared on dimensional grounds. It's proportional to lambda squared in lowest order. Okay. We really know lambda is lambda over h bar is what it should really be if we restored the h bar from this formula. The real dimensionless quantity is lambda over h bar squared. Now let's see, what do I have to multiply an energy by to make that h bar squared e squared? Energy is the same as momentum. It's momentum over h bar that has a unit of, I'm getting confused. We'll do it in 2 minutes afterwards when I don't have that camera staring at me. But you can figure out how many pairs of h bar there really are in the lowest order cross section.
The 5j term in your
Also has an h bar in it. It's S of phi and j over h bar. I erased it, but it's the whole everything has an h bar. Otherwise, I would have different powers of h bar. There would be a power of h bar depending on the number of j's. This way of arranging it, there isn't. Now, I would now like to discuss the generating functional for IPI diagrams. I would first like to define this object, being very careful to define my IPI diagrams with certain cunning conventions to make everything come out right in the end. And then I would like to demonstrate how to construct it in front of the objects we already know, z of j, or equivalently, its logarithm, iw of j. For one particle irreducible graphs, or Green's functions, the sums of all the graphs. I will write this not as a function of a current j, but as a function of a variable which, for reasons that will become clear in around 15 minutes, I will call phi bar. It's a classical variable, just like j. It's a function of x. And this thing is supposed to have some sort of functional Taylor expansion. In fact, I think I'll put an I in. Integral sum on n, integral d4x1 to d4xn over n factorial, gamma n of x1 dot dot dot, phi bar of x1 dot dot dot, just like the functional Taylor expansion of z in terms of j. Likewise, I will define the Fourier transforms of these things, which are the things we really compute in momentum space when we compute IPI graphs, equals integral d4k1 over 2 pi fourth dot 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 gamma n twiddle. Well, sorry. Also should have an exponential in it. I always forget that. Dot 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 gamma n twiddle of k1 kn. And just for convenience, I'll insert explicitly the energy momentum conserving delta function in my definition, just so in later manipulations I don't have to continually divide it out. Now, I will define gamma n twiddle in the following way. I, gamma n twiddle, equals the sum of one particle irreducible graphs with all of our usual conventions. No energy momentum conserving delta functions, no propagators on the external lines, just as before. For n not equal to 2. For n equals 2, I will define it in a somewhat peculiar way, which I will now have to make erase to make space for. for a reason that will become clear to you in a moment. You recall we defined the full propagator by saying G2 of P and P prime equals D of P 2 pi to the 4th delta 4 of P plus P prime. That was our definition of the propagator. The renormalized propagator, phi is a renormalized field, and the unrenormalized propagator, phi is an unrenormalized field. I will now define gamma 2 such that I over gamma 2 of P and P equals D of P. That will be my definition of gamma 2. Gamma 2 twiddle, thank you. Now this is almost our usual definition. As you recall, for example, if I'm summing in our old definition, the gamma 2 twiddle would have been the object we called pi, or perhaps minus pi or I pi, the self-energy operator. That's something I showed you. And in our old definition, we would therefore have D of P equals I over P squared minus mu squared minus pi of P squared. Everyone remembers that? That came from summing up the geometric theories. All I've really done is add, aside from a possible factor of I or minus I, which I haven't bothered to trace out from my old definitions, is add a P squared minus mu squared to the old definition of the two-particle irreducible graph. Sorry, of the one-particle irreducible graph with two external lines. Okay, so all I've done is added an extra term, a trivial extra term determined by the free Lagrangian. Is this clear to everyone? Why I have done it is, of course, still a mystery, but what I have done is just made a trivial addition to the old definition of the two-particle irreducible, of the one-particle irreducible two-field Green's function. Of course, if this is the case, since I've written an inverse here, of course, if I have many fields around, either because I have 42 different kinds of scalar particles or because I have the 4 components of a vector field or something like that, for many fields, this should be matrix inverse. Now, why on earth have I made this dumb definition, extra definition for gamma 2? The reason is simple. With these definitions, if we treat gamma of phi bar as an action, we're dumb. We treat it as if it were an honest-to-goodness action for a field. S. Okay, and compute Feynman graphs in the usual way. It's some horrible non-local, non-linear field theory someone has given us, where all the vertices have terrible dependencies on the momenta. And compute W, or equivalently Z, using true graphs only.
John, that I have a stop for NEPCO. I have a pickup here for NEPCO, and that I went right by Ballinger.
That is to say, we're double dumb. We take this hideous non-local thing as being a quantum action, and then we stupidly only compute tree graphs and forget about higher order graphs. Then we get our two exact W, or equivalently Z. Our errors cancel each other out. Now, why does this occur? Well, it's easy. It occurs because I've cooked it up so it would occur. what's the first step? How do you get the propagator in tree approximation? You get the propagator by inverting the quadratic part and the action and multiplying by I. Well, that's just the definition. That's why I made this dumb definition here. Now you see it. I have made this definition so you get the propagator just by inverting the quadratic part in the action. Good. What about the higher things? Well, let's look at, say, for example, the exact three-point function. Well, we know the structure of that in the kind of theory we're talking about, assuming there is a phi-cubed interaction. I wrote down a formula like that for you once. Remember, you follow a line through, there's got to be a place where you can cut it, etc. for each line. Everything between here and here becomes the exact propagator. Everything here is, by definition, one particle irreducible because it's the last place you can cut the line. This is precisely the simplest tree graph in such, the only tree graph in such a theory. Current, propagator, vertex, current, propagator, vertex, current, propagator, source, I should say, J, propagator, vertex. Likewise, if I look at the 4-point function, the exact 4-point function. Remember, shaded lines mean exact full Green's functions. Unshaded lines mean one particle irreducible means one particle irreducible. Well, let's see. What have I got there? I've got some disconnected parts plus permutations. And those are, of course, what I would get in tree approximation in a theory in which the shaded blob was the exact propagator, to wit the theory under discussion. Then I have practically no blackboard space left. So I'll continue the equation over here. And then there will be graphs where I can cut, putting two lines on one side and one line on the other. So there's an intermediate line, and they'll be, God, it's complicated to write, isn't it? I haven't even shaded them yet. Etc., permuted all the way. And then there will be graphs that I can't cut it in two in such a way so that two lines lie on one side and two lines on the other. And they'll look like, God, most of this lecture will be shading these blobs. Well, there we go. They're all shaded. I've done all the shading I'm going to do. Yes, and there's no etc. there. That's the only one. Now, once again, these are precisely the graphs that would occur in tree approximation, except on all the blobs, I have one particle irreducible graphs. The point is that if you treat the one particle irreducible graphs as giving us effective interaction vertices, to find the full Green function, you only have to sum up tree graphs. You never have to sum up any loops because all the loops are inside the definition of the one particle irreducible graph. Okay, is this point clear? It's an important point because it will enable us to turn the combinatorics of this statement here, will enable us to turn the combinatorics of building up full Green's functions from one particle irreducible Green's functions into an analytic statement. Question? Yes, sir, you have a question. I saw a hand. No. Any questions? This is an important critical point. People should understand it. The marvelous property of one particle irreducible graphs is that if you treat them as if their generating function was a quantum action, and compute things just in tree approximation, you end up with the correct expression for the right Green's functions. Okay.
So the 1 and 3 point there, was that the only one there?
Yeah, that's the only
But you had an et cetera there, but I noticed you erased that. So did that get...
There is no et cetera here. This is the only possibility. You follow through each of these lines. There's, at any given graph, there's the last place where it can be cut.
Okay.
Okay? They make that last cut on each line. What's inside must be one particle irreducible. You can't cut it this way, you can't cut it this way, you can't cut it this way. It's the last cut, last place we can break a line. Everything going up to here adds up to the full propagator. Everything beyond those 3 cut points is the one particle irreducible graph. When you've got 4 external lines, you've got more possibilities. Not only can you cut each of these lines at the last point, but there is a possibility that you can cut the graph down the middle, putting 2 lines on one side and 2 lines on the other. These are the graphs where you can't cut it any which way. This and its 2 permutants, where I switch around 2 of the lines, are the other 2. Okay, is that clear? Okay, good. Yes, sir.
So you define a new propagator that includes all the things you didn't know before.
That's right. It's all in there. I mean, it doesn't make it easier to calculate. Who knows what this object is? Okay, but I'm just pointing out, I'm turning a topological statement of one particle irreducibility into an analytic statement that I will find it easy to handle. The character of the one particle irreducible graphs is that their generating functional, if treated, I've already said it 4 times, is the statement on the right-hand board. Now, this makes it very simple to see the rule that connects gamma of phi to W of j, gamma of phi bar. Yeah, this is going to be a beautiful part. Here, e to the I, W of j, I'll now put the h bar in, just as before, over h bar, plus order 1, plus order h bar, etc., equals integral d phi bar, normalization factor that I don't really care about, e to the I, gamma of phi bar, plus integral j phi bar over h bar. Why did I write down this equation? This is precisely how one would compute the generating functional, d4x. This is precisely how one would compute the generating functional if one treated gamma as a quantum action. I say the term with no loops, i.e. the tree graphs, gives the correct W of j. This is simply the analytic prescription of this thing. The terms of order 1, order h bar, etc. give us the 1-loop, 2-loop graphs, which don't appear in the statement. It says tree graphs only. So I've turned a topological statement that we have the generating functional for one particle irreducible graphs into a statement in words, which using my previous law about counting h bars and counting loops, I have turned into an equation. Is this point clear to everyone, that this equation with the rule about counting h bars and counting loops is the right equation? Now, how do we evaluate this leading term? In the limit that h bar is very small, because we only want the term 1 over h bar. We evaluate it by stationary phase. Furthermore, we don't even have to worry about the determinantal factor in the stationary phase integral, because that is the term of order 1. All we have to do is look for the point of stationary phase. Therefore, to evaluate this integral, we first solve the equation d gamma d phi bar of x equals minus, I'll put it over on the other side, j of x. That is the variational derivative with respect to phi bar of x. It's supposed to be 0. This determines j as a function of phi bar, a non-local function typically. Then, in order to evaluate the remaining part of the stationary phase procedure is once one has found the points of stationary phase, one plugs them into the integral. And the leading term in the evaluation of the integral is the value at the point of stationary phase. Thus, W of j equals gamma of phi bar plus integral d4x j phi bar. This is, of course, going backwards. This is the procedure, not yet the procedure we want. It is the procedure for constructing W from gamma. However, it is rather obviously a Legendre transformation, going from gamma as a function of j to W, gamma as a function of phi bar to W as a function of j. Therefore, it's very easy to invert a Legendre transformation. Oh, this is such a clever way of doing it. You should see how they do it in the books. It would drive you crazy. It is very easy to invert a Legendre transformation. You simply, starting out with W, define which is obviously the true equation you get by varying this thing. That's how Legendre transformations work. Defines phi bar as a function of, of j. Yes, plus, indeed. Thank you. You remembered how to invert a Legendre transformation better than I did. And then one writes gamma of phi bar equals, oh, I wrote it the wrong way around, didn't I? I should have written here, determines phi bar of j. The point of stationary phase is a phi bar point, and this determines j of phi bar. Then to get the function of phi bar, that is simply W minus integral d4x j phi bar. Thus, the whole procedure of taking one particle irreducible graph, of finding the generating functional of one particle irreducible graphs from the generating functional for connected graphs, I should say Green's functions, the sums of all graphs, is simply a Legendre transformation. You differentiate W with respect to J to define the new variable phi bar, and do this. We have turned a complicated combinatoric operation involving getting into the insides of graphs and slicing them this way and slicing them that way and throwing away graphs if we can't cut them in two by cutting if we can cut them in two by cutting a single internal line, into an analytic operation, simply doing a Legendre transformation. Okay. Now there's one point that will be useful to us later, and since I've already got the equation on the board, I will point out, of course, that because of our functional integral, it's rather trivial to differentiate W with respect to J, and you find EVI W of J, dW dJ, which is phi bar of x, equals normalization constant, integral d phi, EVI s of phi and j, phi of x. Or equivalently, since we have a formula, I just differentiated j phi and took out the I. Since we have a formula for this thing also, I could write it in a form that's independent of the normalization constant. Integral d phi, I don't know why I put square brackets up there, EVI s of phi and j, phi of x, over integral d phi, EVI s of phi and j. From this equation, we see that phi bar can be thought of, in some sense, as the mean value of phi averaged over function space in the presence of the source J. What that means in operator terms, I'm not going to work out.
Kyle 1, did you read me?
But this is what it means in function space terms. This defines a J-dependent measure in the phi function space. You compute the average value of phi with respect to that measure, and that is phi bar. Now, this all has, I'm now going to make a sequence of remarks that no one has to understand in order to understand the subsequent parts of the lectures, but may help you to understand what we are doing here, because there is an amazing parallelism that is much exploited in mathematical physics to steal theorems from one discipline and bring them to another, between this thing and statistical mechanics. So I would like to make an analogy with statistical mechanics. Statistical mechanics, there's a parameter in it called beta, which is the inverse temperature in units natural statistical mechanics, in which the Boltzmann constant equals 1. Statistical mechanics is, you begin by defining a partition function that depends on the parameter beta. And the partition function is trace e to the minus beta h. Now, from the partition function, you typically are not interested in the partition function is a nice thing to calculate, trace over the entire Hilbert space of e to the minus beta h. It's a nice thing to calculate, but it is not particularly what you're interested in. One typically begins immediately by computing the logarithm of the partition function, which I've called the free energy. Do you remember what letter is used for the free energy? Someone? Roy, you teach a course in statistical. F? F minus F equals log z. Okay? Now, one differentiates F with respect to beta to obtain the first useful property of a statistical mechanical theory, the average value of the energy, because this expression is trace e to the minus beta h times h over trace e to the minus beta h, and is normally called the energy in the normal sense of thermodynamics, the internal energy of the system. I haven't put in parameters for volumes or chemical potentials. I'll just do it with one beta. If there are more parameters in the theory for chemical potentials or the volumes of the system, you have to differentiate the free energies with respect to them, and you get all sorts of other different things. Now, one then makes a Legendre transformation. It's from turning from a function of beta to a function of E. One says that you take this equation and define F minus beta E equals S, from which one deduces by the standard rules of Legendre transformations, ds dE minus S, I guess. ds dE equals beta. Yes, that is the entropy, ds dE. Yes? Okay. Everyone knows this, right? This is what you learned as babies. It's old thermodynamics, where you all went crazy for the first time in your life having to take partial differentiation seriously. We all Now, there's a parallelism there is an obvious parallelism between these equations. Instead of a statistical mechanical sum, trace, we have a sum over function space, which gives a function, which now you know why people call it z, called z. We have IW equals log z, just as we have minus f. There's an I in this one and a minus sign in this one because there's a minus sign here and there's an I here. We define dz, dj, not dz, dw, dj, equals phi bar. Just like we defined df, d beta equals E, the energy. And then we make a Legendre transformation. Gamma phi bar equals W of j minus integral d4x j phi bar. Just like this Legendre transformation here. The only thing that's in any way different is that here we're just differentiating with respect to a single beta, and here we're differentiating with respect to an infinite number of variables summed up in the function j. Of phi bar. J as a function, this determines j as a function of phi bar. Just as here, you have to rewrite the free energy as a function of the energy rather than the function of the temperature, the entropy equation. And we end up with d gamma d phi bar equals minus j. Therefore, there is a perfect analogy, aside from the fact that in one case we have an infinite number of variables characterizing our thing, j of x at every space-time point x, and the other case we have a single temperature beta, between inverse temperature beta, between the operations in statistical mechanics and the operations I have just deduced in quantum field theory. We could make things, if you know, this is a pretty much straight Helmholtz statistical mechanics transformed into quantum language, in the quantum language. It's in fact a bunch of equations Helmholtz did write down, except instead of trace, he had integral dp dq because he was summing classical systems over classical phase space. The Gibbs's variant, as you know, introduced in addition to beta a lot of other parameters, chemical potentials characterizing the volume of the system, external magnetic field, and so on. And he just rattled along. He differentiated with respect to those and got their mean values. And then when he made this Legendre transformation, he had a sum over all of his variables. So Gibbs's formulation, which has a sum over a bunch of objects, a bunch of parameters other than the temperature, looks even more like what we have here. Indeed, if we wanted to consider the statistical mechanics of some magnetic system in an arbitrary spatially dependent magnetic field, which would interact with the system, we would get formulas with functional derivatives and integrals in them, just like these formulas here, because we'd have to differentiate with respect to the magnetic field at every point. So you can make the analogy look very, very close. In fact, once you make the Euclidean rotation, the analogy is perfect, because then you really do have either the minus something. You are summing over all possible configurations of a classical field, just as in classical statistical mechanics of a field theory in 4 dimensions, 4 space dimensions. And it is, in fact, quantum field theory is identical to classical statistical mechanics of a field theory in 4 dimensions, with 1 over h bar playing the role of the temperature. No, h bar playing the role of the temperature, and j playing the role of some external field that couples to the system, like an external magnetic field couples to a magnetic system. This is, in fact, not very useful. All it tells you is that classical statistical mechanics of a classical field theory in 4 spatial dimensions is a very complicated problem, which we are not going to solve. However, it is a very useful analogy for people who want to prove things about field theories in smaller than 4 numbers of space-time dimensions, where this classical system is not so complicated and in some instances has been solved, and then they can, or has rigorous theorems have been proved about it, and then they use precisely this analogy to prove rigorous theorems about the corresponding quantum field theory in 1 + 1 or 1 + 2 dimensions. But that's a long digression, which isn't written down in my notes. I just got carried away with enthusiasm, which happens. Quantum electrodynamics in a covariant gauge. If I define gamma phi bar equals gamma gauge invariant. No, I won't say it's gauge invariant. I'll just call it gamma GI for the moment. Plus 1 over 2 alpha integral d4x d mu a mu bar squared. Then I observe from this equation delta gamma gauge invariant of phi bar under a gauge transformation equals 0, because the delta of this term gives me all that I need. So GI was not bad notation. It does mean gauge invariant. The action, the gamma, the generating was sometimes called the effective action. Phi bar field, and of course we could consider something with 20 billion kinds of charged particles that have various interactions among themselves. They all have well-defined gauge transformation properties. I'll write them down for an infinitesimal gauge transformation. That's an infinitesimal gauge transformation, delta chi, an arbitrary function of space and time. Psi goes into psi minus IE, delta chi psi. That's either the IE chi expanded out to first order and delta chi, etc., whatever other fields you have in the system. I'll write this in the generic form by assembling all of my fields into a big, enormous vector, phi. Boson, Bosch, Fermi, stick them all together in a great big column vector, and writing this simply as phi goes into phi plus some operator, A of phi, on chi. The only fact I'll use in the demonstration is that this is first order or zeroth order in phi. That is to say, this is either linear in the fields or zeroth order in the fields. For a mu, A is simply the differential operator d mu. For psi, it is multiplication by IE psi, etc. Now, since I'm going to use this for renormalization theory, I should tell you whether these are renormalized fields or unrenormalized fields, or whether these are renormalized charges or unrenormalized charges, and it doesn't matter. You can either think these are unrenormalized fields and the bare charges, or that these are renormalized fields to some finite order in perturbation theory, and we are studying the effect of a gauge transformation on the action to get constraints on the divergent parts of graphs, which we will have to cancel off with counter terms in the next order. Just doesn't matter. We have a set of fields. How we've defined E, so it's a parameter that defines the gauge transformation, and this is what happens. I will also assume my action in my typical case will be a gauge invariant action plus some parameter, 1 over 2 alpha. Perhaps I called it minus 1 over 2 alpha, but that's neither here nor there. It's not going to affect the argument. If we're working in one of the covariant gauges, like Feynman gauge. When I make this infinitesimal gauge transformation on the field, S of phi goes into S of phi. The gauge invariant part doesn't change. And from this part here, I have 1 over alpha, because it's a square, integral d4x del squared chi. I will write this as S of phi plus integral b of phi chi d4x, where b of phi is also first order or less in phi. It's in fact, as we see, just d mu a mu del squared. Oh, it's blocking your view, certainly. The only thing I will use in the argument is that A, although using it for this particular case, are 3 things. One, A has a stated property, B has a stated property, and thirdly, that the gauge transformation doesn't change the measure in function space. It has determinant 1, which is obvious in this case, since it's just adding a constant to A. And for every psi and psi star, we just have a little rotation. Now, therefore, the argument will be generalizable to any case obeying these 3 conditions: linearity of A, linearity of B, and linear or 0th order, and doesn't change the measure. Why do I want these 3 things? I want these 3 things because this means that if I make this infinitesimal transformation and think of it as an infinitesimal, well, first, the fact that the determinant doesn't change, the measure doesn't change, which I'll also write down as an equation. d phi goes into d phi, it's gauge invariant, means that if I make a change of variables, if I make this transformation as a change of variables in my functional integral is not going to change. Thus, e to the I w of j, which equals some normalization constant, integral d phi, e to the I s of phi plus integral d4x j phi. Now putting the source term explicitly, I'll just change the variables. You change the variables and integration doesn't change it. So this goes into what's the change? Well, the change is very simple. I just pick up a little extra term from this b thing here in the exponential, and I pick up a little extra term from this term because this Duracell ain't gauge invariant. So I will obtain normalization factor, integral d phi, plus, excuse me, e to the I s of phi plus integral d4x j phi. Now here comes all the extra terms, and since they're first order in delta chi, I can expand out the exponential and bring them down. What?
You turned e to the IW plus an integral, which is e to the IW.
That's right. That's going to be the first term in the expansion.
The e to the IW that's just after the arrow.
That's right. That's the 0th order term. And then there's the first order term in delta chi, which I'm expanding out. And that is, I see here, from non-gauge invariant part of the action, I, b of phi, delta chi, better call it a new variable, d4y, plus j, a of phi, chi. Okay, that's the change in S, that's the change in this, I've expanded it down. On the other hand, it must also, by the same token, since this is just a change of variables, go into e to the IW of j plus no correction. Therefore, this term down here must be, did I make a mistake?
No, I just can't see what the very last thing is.
Sorry. And I should call the integration variable y so you don't confuse it with the x up there. I, b of phi, delta chi, plus j, a of phi, delta chi. Delta. Let me rewrite it.
I'm going to rewrite the whole bracket.
Yeah. Yes, okay. Good idea. Inside the integral times I. Integral d4y. B of phi delta chi plus a of phi j a of phi delta chi d4y. Okay, is everyone happy? I've just expanded an integral exponential out to 0th order and 1st order delta chi. On the other hand, the change in e to the IW of j is nothing. As I said, I mean, it doesn't change at all because all I've done is change variables, so therefore this additional term must be 0. What I induce by a change of variables in an integral is nothing. Therefore, the explicit change in the integrand must integrate to 0. Good. Thus, we have an equation. N integral d phi e to the is of phi and j integral d4y b of phi delta chi plus j a of phi delta chi equals 0 for arbitrary delta chi. That simply says we know how our integrand changes under a gauge transformation, and since we could reinterpret a gauge transformation as just a redefinition of our integration variables, it doesn't change at all. Now we come to the key point. A and B are linear in phi. Therefore, when I have an integral like this, I can replace phi by its mean value, phi bar, in that expression. There'll be a multiplicative factor, but so what? Equals 0. I'll just take out the multiplicative factor. That follows from the linearity, and that phi bar is the mean value of phi. Of course, if I had a phi squared, I couldn't make that substitution. The average value of phi squared is not the average value of phi quantity squared. But if everything is linear in phi, that's very easy. Everyone happy with this equation? Now, we know what J is. J
Remember what are we going to get over before y?
Delta chi of y, d chi of y.
The bracket here.
Yeah.
Should be brackets in
No, doesn't matter where you. Well, I'll put them there, put them there. Okay, are there other questions? Everyone happy? Good. Because now comes the magic point. J is, as you may remember, minus d gamma d phi bar. Therefore, I have, bringing one term onto the other side, integral d4y d gamma d phi bar A of phi bar delta chi equals integral d4y b of phi bar delta chi. Now, what is the meaning of this equation? This tells us how gamma phi bar transforms under gauge transformations. That is to say, if I write down for the phi bars, if I consider the gauge transformation for the phi bars, mean fields, that are exactly the same as the gauge transformations I originally had for my quantum fields, to wit, delta phi bar equals exactly the same rule, A of phi bar delta chi. All I've done is replace phi's by phi bars, a's by mu bars, psi's by psi bars, all the way along the line. Then, of course, the change in gamma, which is only a functional of the phi bars, is integral d4y d gamma. This is the chain rule of differentiation.